Okay, so looking for graphing today. Why do we graph stuff? We often make graphs just because it's a quick way to analyze data. You can kind of see how an object is moving or something like that. So that's why we graph stuff. Um, Position time graph for an object moving at a constant velocity is a straight line with a constant slope. Okay, we're going to do one and we're going to see what this thing looks like. But what I wanted to kind of get through before we look at this too much is stuff that every graph needs. So every graph needs a couple things. It needs an appropriate scale. And by appropriate, I mean appropriate so that your graph kind of fills the axis, at least half of the axis, if not more. So if your graph is, if you've got like, a graph like this and your actual line is kind of like there, then it's too small. You got to, you need to kind of focus in on this part and sort of make it all bigger. So choose an appropriate scale so that your line kind of fills the axes, or at least more than half of it. You want to have properly labeled x and y axes. So the y-axis is over here, the x-axis is over here. Include things like units and direction and stuff like that. Appropriate title is y versus x format. So whatever's over here on your y-axis, whatever's over here on your x-axis, that's what's going to appear in your title. Line of best fit. In general, in physics, that's going to be a straight line, not connect the dots, but a straight line. And a legend if there's more than one line. So, you can go with sort of different colors if you've got these different lines, and then have a legend over here that says, the green is this, and the purple is this, and the red. Whatever they are. We will see that sometimes in physics, not all the time, but if appropriate, put that on. All right, so let's try this. You can read through those steps a little bit longer, a little bit more on your own, but what I wanted to do is to actually try this out to kind of see what it looks like. So let's draw a set of axes here. Oh boy, that's no good at all. Okay, let me try this one more time. All right, that's a little bit nicer. Okay, so let's say we've got that, and what we're going to have on here is position. In general, time is going to be our x variable, our independent variable. Position is what we're measuring, so that's our dependent variable. Hopefully these things are familiar. Time in seconds. The normal thing is to label it what it is, but then put the units in brackets. So meters and seconds in this case, just because that matches what we've got up here. If there's a direction, we need to include that as well. Okay, something that sometimes people, get a little tripped up with is they think the y-axis, because it's kind of pointing this way, that should be north. That is not north. The y-axis, whatever it is, it's whatever direction is kind of stated, I guess, here. So it could be south or east or west or any direction. Don't think that because the line is moving up or something like that, that it's going north. This just represents whatever that direction is. This isn't going to be a very, very accurate graph, but again, we're going to try to choose our scale so that it kind of roughly fills this. So let's go, 1, 2, 3, 4, something like that. 1, 2 is kind of buried in there, 3, 4. And then similarly going up the y-axis, we could kind of maybe go, 10, 20, 30, 5, 10, 15, 20. So let's say here's 20, 15, we'll put 5. We'll kind of make that into the 5 right there. 10 is kind of buried under here, but we'll sneak it in there. Obviously, if you're to do this for real, you're going to use like graph paper if you're doing it by hand, or do it on computer, that's fine. I'm happy anytime we do any graphs, you can do them on a computer. You are welcome to do this part on the computer, have it print the dots, and then just print it out and draw with your hand or something like that if you're having trouble getting a line of best fit. Let's go ahead and stick some points on here. We'll go back to blue. So we've got a point right here at 0, 0. At 1, we're just under 5, so let's say right there. At 2, we are just above 10, so somewhere there. 3, it looks like we are right at 15. And then 4, we're just shy of 20, something like that. There's our line. I'm not going to connect the dots. What I'm going to do is stick a ruler down, and hopefully this doesn't go weird on my iPad here. I'm going to stick a ruler down and draw a nice line of best fit on this thing. Something that you can see with a line of best fit, let's go green here. We've got one dot that's kind of like above the line and one dot that's kind of below the line. What we should see is an even number of dots on either side of the line. Hopefully, ideally it goes through most of our points. But if we've got points like this guy that is, one on the low side, we should have one like this guy over here, one on the high side. Okay, so kind of an even number of points on either side of the line to make our line of best fit. Last thing we're asked to do here is to find slope. We're going to choose any points off of our line of best fit. Okay, 0, 0 is a fan favorite. The line of best fit does not need to go through 0, 0. Okay, it can go through any of the points, wherever your data is. But in our case, I'd say it nicely goes through there. It nicely goes through there. To find slope, I'm going to choose not the 0 point. I'm going to choose this guy. Well, you know what? I'm not going to choose that guy. I'm going to choose this guy just because the points, we've got nice data. So we have nice data for this point, nice data for this point. So let's do that. For finding slope, remember from your math class, y2 minus y1 over x2 minus x1. If you think about what that stuff is on this graph, our y-axis is actually position. Okay, and position, remember, is d. So this is actually d2 minus d1. Remember we talked about that before? That's actually delta d. And the x-axis is time, so this is actually t2 minus t1. That's, again, delta t. Okay, so this thing right here is actually delta d over delta t. Okay, so that's what we're using for slope. We've seen that before, and this is these are vectors. I should throw my vector signs on here. That thing right there is actually average velocity. Okay, so something to remember here. We're going to go ahead and find the slope in a sec, but the slope of a position time graph, and I didn't put a title on here, I should. This graph is going to be our y-axis, so position, versus our x-axis, time. Okay, so this is our positions, our y-axis, x is our time axis. I know what I was saying. The slope of a position versus time graph is average velocity. Okay, so that's an important little detail. Let's see if I can finish this off down here. So we're going to use 15 is our D2 and 0 is our D1. And let's see, coming kind of down this way, 3 and 0. So 15 minus 0 is just 15. 3 minus 0, that is 5. The y-axis is in meters. The x-axis is in seconds. So my units are meters per second. Okay, so there's the answer. Okay. If I was going to do that kind of nicely or write it nicely, I would say V average is 5 meters per second. And we should put a direction on here. And remember what I was telling you at the beginning. Sometimes people get confused and they say this direction is north, this direction is east. This line here looks like it's going northeast. This is not northeast. It is whatever direction is here or here. Whatever direction is listed as the positive direction on the y-axis. Okay, so this direction is just east. Okay, so there it is. And again, maybe I'll put a big thick box around this thing. I lost it. Anyways, hopefully you caught that. You can back up the video. There's our line of best fit. Oh, there it is back. Phew. There's our line of best fit and the slope. What did you just find? You just found average velocity. Good. Here's another one. So a little bit more complicated looking graph. Again, there's no title on this one, so we could say position versus time. On this one, I wanted to think just a little bit about what's going on. If you look at a position time graph, if we find the slope, but there's no points given here, we're not actually going to find the slope, but if you can imagine, if we found the slope of this part, I would get a relatively steep slope. What that means is I would get a big number. Okay, so there's no numbers given here, but let's just imagine for a second. It's like this would be 10 meters per second. If I find the slope of this guy, it is not going to be as steep. I'm not going to get as big of a number. It might be, hold on. Whoop. Everything's going crazy on me, you guys. So let's see if I can do this one more time quickly. This one here, we had 10 meters per second. This one here, I can't remember if I started to say what it was, so let's just say 7, something less than 10 anyways. What I can see is from this really steep line here in part A, I've got a steeper slope. I'm going faster, what that means. So steeper slope means you're going faster. You could say as well, I'm going in that direction. So the direction of this velocity is south. Here, the direction of the velocity is still south. Anytime I get a positive slope, I'm going in that direction. If, however, I was to look at this one over here, I would get a negative slope. Okay, so if I was to find that slope, it looks like maybe, I don't know, maybe similar to line B. So maybe it's negative 7 meters per second. Okay, what that means is negative 7 meters per second south, that is, let's say, or positive 7 meters per second north. And we've seen that before as well in some of our examples. If you're going negative 7 south, you're going positive 7 north. Okay, so the negative slope means I'm going the opposite direction to what is on the axis over here. Oh. If I found the slope of this guy looks even steeper than A maybe, so maybe this is, again, negative 10, maybe negative 11 or 12 or something. So I'm just going to go ahead and say 12 meters per second. Remember, negative south or positive north. What about the slope here for C? You can shout it at your computer screen or your phone or whatever you got. The slope here is actually 0. The slope of a horizontal line is 0. That's 0 meters per second. What that means is I'm actually stopped. Okay, so I'm actually not moving. So in A, I'm going fast and forwards or south. In B, I slow down. I continue to move at a constant speed or constant velocity, but I'm going slower than I was in A. Then I stop for a short time. Then I reverse very quickly in D. Then I continue to reverse in E, but I'm not going as fast. And that's it.